Hello everyone, I'm Yuanbing, a PhD student from Tsinghua University. It is my honor to give this talk and thanks for your attention. Today I'd like to introduce our recent work, Efficient Algorithms for Crowd-Aided Categorization. Let's start with a tiny example. Given a hierarchy and a set of objects, our goal is to find the most suitable category for each object and minimize the cost. That is, the number of questions to ask humans. Now we have a hierarchy of different places in the world, and I want to know where this photo is taken. A simple method is to ask questions in a top-down manner, according to the hierarchy. That is, in the first step, we stand at the root of the hierarchy, node Asia, and show two options, East Asia, South Asia, which will direct us to next potential node. According to the answer, the right one is East Asia. We then show questions about East Asia and show three options, China, Japan, South Korea. Finally, we ask questions at node China, show two options, Beijing, Shanghai, and get the final answer, Beijing. Thus, we totally asked three questions. What if most of the photos are taken in China? Then we don't need to ask questions from the root of the hierarchy. Instead, in the first step, we directly ask questions at node China. This time, we show three options, Beijing, Shanghai, and none of the above. If the replier chooses the last option, then we should ask questions about other nodes which are not in the subtree rooted at China. Because most photos only need one step to get the final answer, the average cost is close to 1. Compared to the former method, we can save a lot if we know the probabilities and make good use of them. Now let me introduce the first definition, multiple choice question. A multiple choice question corresponds to a node in a given hierarchy, and the bridge is a partition operation, which removes all the incident edges of the selected node, say China node, including the edges connected to its children, and also to its father. The right picture shows the partition operation. For node China, by removing edges, we get 4 subtrees. The first two are its children, Beijing and Shanghai. The third is itself, node China. The last one is the subtree containing its father node, East Asia. And the 4 subtrees produced correspond to 4 options in the left picture, respectively. We use phi t u to denote the subtrees produced from conducting the partition operation on node u. By repeating the partition operation in the subtrees produced, we would construct a decision tree to ask questions from the given hierarchy T. The numbers labeled below nodes are category probabilities. In a decision tree D, every leaf is a category in a given hierarchy T, and each internal node of the decision tree D corresponds to an internal node in a given hierarchy T. For a node U in T, we define its probability as the fraction of the objects whose target categories are node U. For a subtree in T, its probability is defined as the sum of all probabilities of nodes in that subtree. It is easy to see that for one target node in the decision tree, the number of questions to ask humans equals the depth of the target node. And the cost is defined as the average questions to ask over all objects, which equals the sum of product of probability and depth of every leaf node in the decision tree. However, even if we know the probabilities in advance, constructing an optimal decision tree is NP hard. The question node selecting criterion is not trivial. We proposed a greedy algorithm, that is, choose a question for some category U0 among all internal nodes of T, which makes the heaviest resulting subtree among 5T U0 as light as possible. Regard the total probability of a subtree as its weight. And recall, 5T U0 denotes the subtrees produced from the partition operation. This greedy strategy is a crucial contribution of our work, which brings the large cost savings. Look at the example on the right side. The upper one has the max probability of 0.5, while the lower has 0.7. Thus, we'd prefer to choose node China as the question node, rather than node India. The time and space complexity of the greedy algorithm is big O of n squared and big O of n, and it is proved that the decision tree constructed by greedy is less than or equal to twice the cost of the optimal decision tree. So far, we have assumed the probabilities are known in advance, while it is not the case in many real-world scenarios. The uncategorized objects are processed in a stream fashion, and thus, we can develop an online algorithm to learn the category probabilities. A simple method is to record the categories of all processed objects and use fraction as probabilities. But this method is subject to adversarial sequences, which may lead to rather expensive cost. Therefore, we proposed a more robust method, following the perturbed leader, which combines the fraction and exponential perturbations. The example on the right side illustrates the procedure. We record the number of processed objects for each target category, plus an exponentially distributed perturbation to get the weight, and normalize all the weights to be probabilities. Now let me introduce the performance of our proposed algorithms. We conducted experiments on two datasets, Amazon and ImageNet. Amazon is a dataset containing millions of e-commerce products, and ImageNet is a dataset of various kinds of images. We compared our algorithm with the state-of-art method, IGS, which is published in Sigmod 2019. For fairness and to avoid too many options in one multiple choice question, we developed a binary version of greedy called a greedy binary. For synthetic data evaluation, we randomly sampled 100,000 objects to test for each dataset, and the results are shown on the left two figures. Note that we also made extensions to our algorithm for batching. For one object in each round, k multiple choice questions are issued. When k equals 1, round equals cost. For evaluation on crowdsourcing platform, we prepared 100 objects and evenly divided them into 5 stages to update probabilities and construct new decision trees. It can be seen that our algorithm performed increasingly better as more stages are finished. Also, the overall accuracy and average crowd cost showed the effectiveness of our method. Synthetic and real-world experiments demonstrated that our method clearly advantages the state-of-art method. Okay, that's all. Thanks for listening. If you have any questions, please feel free to ask.